So today we're going to talk about non-stationary search, and a particular context of that non-stationary search would be learning about the quality of a match over time. So until now we've assumed everything's stationary, but there's no reason to believe that's the correct characterization of the situation in a labor market match, especially in the short run. Maybe in the long run, people get it, and maybe things are quite stable, but if things are changing, and if they're changing in a way that's not necessarily easily predicted, then this might give rise to interesting dynamics that could affect people's behavior, including their reservation wages. So that's the notion today. So we'll start with a review of last week, and then I'll talk about some of the fundamental ideas behind non-stationary search. And some of this is in the paper by Rogerson, Scheimer, Wright, but some of it is elsewhere, so I'll give some other references. Some are online. And I'll give you some examples of where this idea has been implemented, and the most important example is the Jovanovic model, which I quote the original paper, but this paper's been adopted and adapted many, many times in many settings, including in the famous macro textbook by Lundquist and Sargent. So there's a whole chapter or sub-chapter on this model. So it's obviously something that's been, Jovanovic is one of his most important contributions. He's a professor at New York University and has worked in IO and macro and labor. And this is a really great paper. Okay, so let's just review. Actually, I think I'm going to just skip last week because it was kind of the end of the topic. But we'll come back and review some of the ideas. I'll go right into the fundamental ideas behind non-stationary search because it's there's a lot of material here. But if you remember, up until now, we've had stationary search as the paradigmatic basis for all the models. The idea is that the distribution a worker faces when she decides to stop searching and to accept a job offer does not change over time. And for that reason, the derived reservation wage doesn't change. So the optimal policy is time invariant. It's really just a function of the underlying taste and distribution parameters of the model, and it has nothing to do with calendar time or time elapsed. Okay, and that's the idea would be, if you remember all the readings you've done, especially in this article, using a dynamic programming problem is the way to go, and we end up in this optimal stopping problem. We understand that when the draw exceeds a certain critical value, you basically accept the job under many, many different conditions, including future severance and productivity changes, on-the-job wage offers. That was the last stop of the course, the famous Burda-Mortensen model and the variations thereof with heterogeneity all have the same characteristic. Okay, so you see there's no time subscript. The only implicit time is expressed in beta. And this is the discrete version of the model. If you remember, in continuous time, we had a model that had a continuous discounting and random arrivals according to a Poisson type of setup. Going back to the original model, we had a discrete one offer per period. The very most basic model would imply the same kind of flavor, except now beta is much more explicit. And but you still have this today and tomorrow view. Basically, do I accept the job at some wage W? If it's greater than WR, or I keep searching with the prospect of waiting a period and getting a draw. So that's the implicit cost. Okay, and we had two ways of expressing that. Just to remind you, you should be able to derive this in your sleep for the exam because it's kind of an easy problem. Everything else builds on this sort of, exactly one arrival per period, no uncertainty about that. Okay, so just keep that in mind. This model doesn't have any separation either, so this is the simplest way of thinking about it. There's a nice way of thinking about this formula. You can think about it as a mapping of the current situation into the future situation, or think of it as taking the expected future outcome described by a distribution and mapping it into a decision variable today, and that would be WR. And there's no reason to think that WR is time invariant in any particular instance. We basically impose that, but if you go back and think about it, you could think about WR as being a number you compute today given some assessment of the distribution of wages you're going to be facing in the next period, and this WR feeds into the decision you take in the next period. Therefore, in some sense, the WR on the right-hand side and the left-hand side are assumed to be the same, but suppose they weren't. Suppose you move into the next period and you basically recompute a WR given your encounter. So there's no reason in an out of equilibrium sense that WR prime and WR have to be the same. Okay, so you could imagine the solution to the problem, those two are equal, but suppose they weren't. Suppose you started with WR, you went off and you selected, you encountered a wage, and you basically recalculated it using the same formula as before. You can imagine this as being sort of a mapping. So you can imagine this being sort of on the way to a convergence, which would be the steady state reservation wage chosen. You can imagine this as actually defining a path of wages over time. So, and in the paper, Scheimer, Scheimer, Wright, they make this point, which is interesting, that suppose that after n periods, you had basically, it was over. So you had no more wage offers. You just basically got B. So you could actually go backwards n periods and solve for the path of the reservation wage in each period that would be consistent with the last period being faced with B with certainty. Okay? So think about that path of reservation wage is certainly not stationary. It would be a non-stationary type of solution. It's actually a trajectory of reservation wages. Okay, so under those conditions, this is not the original problem, but this is one that actually introduces time explicitly. You could imagine the worker kind of groping for the reservation wage that's right, but then even though the worker knows the distribution of wages in every period, would have like sort of n chances working backward. And this would be the implied time path of the reservation wage going forward. And it would be declining, okay? So this is kind of one example of a time-dependent and obviously a finite path of search behavior. And we could put this in a whole class of problems called non-stationary search, meaning that somehow the decision policy variable is time dependent, or it could be state dependent. It could also be state dependent. So in my example I gave, it depended on how much time we had till you got your benefits you got cut off from the offer distribution, or you can think about it as a situation where in n periods you move to Hatzvia. So you move off, which doesn't exist anymore, but it's the idea. So somehow putting a time limit on the search problem already puts a certain non-stationarity into the problem. And you could also think that maybe, depending on some state variable that I observe, I might condition that distribution on the state variable. That would also imply a non-stationary type of search. So if I thought that the search distribution or the wage distribution I'm confronted with depends on the business cycle, and the business cycle is non-stable or even non-stationary, or it could be cyclical, state variable. So in some sense, if there's any sort of time or state dependence, it would not be of the class of strictly stationary search models we've dealt with. So there's a lot of degrees of freedom you can add to this problem suddenly, you know? Because we're all finite-lived, and in some sense, everyone's search is kind of non-stationary in some fundamental sense. Okay, so what do you think? Give me, I just gave you some examples, but what else could matter for non-stationarity? Does anybody have any sort of good ideas? I mean, I already said one. I said a couple, actually. Time or state dependence? Well, I just told you finite time, right? So retirement, end of benefits, some looming terminal condition in the problem. Anybody else? This is a huge audience, by the way. I'm searching. Anybody have any ideas? So maybe the distribution isn't constant. We've always assumed it's constant, but why does it have to be constant? Why would it not be constant? I mean, we kind of assume that that's the fundamental bedrock of the model, is that the worker has this notion of the density function of the wage offers that she's facing. Is that realistic? It might be.
I mean, yeah, so to some sense, like, I mean, for the university, for example, like always like the schedule group are advertised and everybody knows what to expect. So
yeah, but
common jobs as well, I think.
Yeah. But do you really know? I mean, just think outside the box. Why would F not be constant?
Depends on labor market conditions.
Yeah, it could depend on the labor market. It could also depend on, yeah, it could also depend on, these are macro things. What about the micro? What about you? You're the searcher. What do you think?
Education.
Yeah. But why would that change?
It looks different for somebody with a university degree than it looks for somebody who...
Yes, but that's like that would, for individuals, that would be a non-changing unless you thought education depreciated.
Or as you earn more education, the wage offer distribution available to you changes.
It could change, that's right. And maybe the converse of that would be if you were unemployed a long time, your wage distribution shifts downward. Okay, so maybe you lose skills. That's a widely cited reason, is that your unemployment history might affect your employability and your wage offers. People might make different offers to you because you're unemployed. Remember, that was one of the things we assumed away in the search, on the job search model. It's probably not quite correct. Maybe people have an unreasonable view of their own ability. You know, people may overestimate their talents. They may have had a great job, they lose their job, they assume, well, I can get another one like this, and maybe the world has gone past them. You know, this can happen. And you're facing, so this is a fairly commonly held view that people may overestimate their wage offer. But you don't want to underestimate your wage offer either, so you can't criticize them. Maybe it's just maybe there's some sort of learning going on, okay? So that's another thing we talk about, learning. So the state variable might be the last offer you get, and then under some conditions it might come from one distribution, it might come from another distribution, right? So maybe if you get a lot of bad offers, it may mean that your distribution has shifted down and you need to revise your problem. Otherwise, it might just be bad luck. The models we've dealt with to date are all telling you it's all bad luck. Okay, the last thing is this notion that maybe if you become unemployed, your tastes change, you might actually think, this is kind of okay, I can deal with this, this is my lot, you know, my fate. Or you might actually lose productivity the longer you're unemployed, the less contact you have with other people of your type and job experience, job classification that could actually hurt. And, you know, technical progress moves on, new things happen. So all these things could matter. And under those conditions, the reservation wage would not be constant, even for the most rational person, you know, and then you have to just define what is rationality. We're always kind of assuming people are pretty clever, and what's happening is their environment's changing and they have to learn about it, or maybe it's just changing and they have to deal with it. Okay, but again, this is the frontier of what people are talking about. So let's think of some examples. I mean, Professor Wright, pretty prominent guy, author of this paper that I keep telling you about. He wrote a paper when he just got out of PhD to explain macroeconomics. So one of there are some fundamental facts about macro, and this is very controversial. We know that unemployment is very persistent. Okay, so unemployment, especially after a bad shock, if you look at the American data, it looks like a EKG. Basically, there's a big move up, and it goes slowly down. And Robert Hall has written a paper on this, which is really amazing. The rate of decline of unemployment is fairly stable. You know, so the Great Recession, a big heart attack, and then slow persistence. Recent recessions, and you know, the whole post-war history, the same kind of absolute rate of change of unemployment over time. Even the pandemic, right? The pandemic had a big jump in unemployment, but not as big as the Great Recession, still a rate of decline. So one idea would be that Wright said is that these people lost their jobs because of a demand or a supply shock, and they just have not revised their reservation wage. The reservation wage should be revised downward. They should be more ready to accept jobs, and that would, you know, to the extent that the reservation wage is moving slowly, people aren't picking up the jobs quickly enough, given our view of the bathtub. So these people are just kind of thrown out there, and they have to sort of sort things out. It is a fact that wages that we observe that people earn are also very persistent, much more persistent than the price of goods or quantities. This goes back to Keynes, right? Sort of real wages, but especially nominal wages, seem to be persistent and rigid. Okay, so remember, the wage is a complicated object. It's not a Marshallian labor supply and demand like in my other labor course, but it seems to be subject to maybe a posting by employers and behavior of workers. Okay, so that was kind of, you had a question, Paul? Okay, so search model would imply that workers, this is the problem that people have with this model, because it only really kind of works if it works the way I told you, I think, because you have to be kicked out of the job, and then because your reservation wage doesn't adjust to accommodate this new macro situation, you tend to be unemployed for a long time, okay, or longer, because many people are not unemployed for very long. That's a fact. What's really a problem is the overflow in the bathtub. So the problem with back then, they kind of wanted to say that workers were quitting into unemployment, and that's just not true. So in some sense, the right approach, if you take the pure search model, would say my reservation wage is stubborn, the wage distribution shifts downward, I'm just not accepting job offers. But we don't really see people quitting into unemployment, because unemployment is not a pleasant situation. So obviously there's some tension between this view. We don't observe pro-cyclical quits into unemployment. We observe, if anything, we observe a slow resumption of employment after a big surge in flows into the bathtub. And we also observe, and this fits with the Pissarides model, because of this increase in unemployment, we have a congestion problem. So we have a lot of unemployed people per vacancy, so vacancies are down, unemployment's up. So obviously if you're unemployed, you're gonna have a hard time getting an offer anyway. So it's not just the reservation wage, it's probably a good mix of the reservation wage being rigid, but also the contact probability, as predicted by Mortensen Pissarides or by Pissarides, goes down. Yeah.
So So if we say that workers don't adjust their reservation wage after the shock, does that imply some sort of irrationality? Or because you mentioned that if they were rational, then the reservation wage would change over time and kind of adapt to.
Well, that's what Wright tries to pick up on his paper. So you can think about if workers have to learn about their distribution, and maybe the distribution is a composite of a macro part and a micro part, then maybe when they first become unemployed, they say, well, I think I'm still pretty good, and I think I could still get a good job offer. I don't believe that the shift in the macro distribution has occurred. I have to learn. I have to be sort of beaten into submission. That's one view of this. So this whole lecture is based on learning, sort of taking new observations and adjusting, maybe using a Bayesian principle, adjusting what you believed before. Yeah.
Yeah, and is it possible to kind of untangle if declining unemployment after a shock is due to adjustments in reservation wages, or in kind of the overall economy kind of getting better from the shock and kind of
It's hard. Yeah, it's hard to do that because we don't have we have surveys of reservation wage. We don't know if people are necessarily understand what that means, and it's a very complicated concept because every wage offer is connected with it's a wage offer combined with some job. So the job has amenities which may make the effective wage higher. The pecuniary value of the job higher because you have a nicer place to work, or it might be a really terrible job with very bad hours, and with that reservation wage that people state in a survey might not be very easy to connect with that. But yeah, I mean, all I know is that they move very slowly, and this model, you can make this model into a straw man and just criticize it. Because, in the old days, they used to say, well, African Americans have a higher unemployment rate than whites. Therefore, they must have a higher reservation wage. Well, that's just baloney. That's just you're trying to stick the theory by not really taking it seriously. So, you have to be very careful. But there is evidence that these things are very persistent, which tells me that maybe you need to combine this with a model of maybe aggregate demand causing the initial shock into unemployment, or maybe a bad supply shock like we're experiencing now, especially in the United States, probably more of a demand shock. And then this would also explain why in booms, workers willingly work for wages that don't look like maybe they're higher, but maybe they don't get the real wage right. Maybe real wages are kind of stable, but they think they're getting more money, but in fact the real wage is not rising very much. So all these things were kind of right, I think, was trying to push the macro side. And this kind of is in line with this old literature of Robert Lucas, thinking of the Phillips curve as basically based on calculations or false expectations, erroneous expectations of the price level. So we move up the Phillips curve, inflation is rising, workers think they're getting more real wages because they've miscalculated. So this Wright model is in that tradition. And when workers figure it out, finally they'll raise their nominal reservation wage, and they'll know their supply curve effectively moves again to the left, if you think about it that way. So this could be about learning about your mistakes, observing some mixture of something that's really relevant to you in a real sense and something that's just a nominal sort of price level change. This is Lucas's 1973-72 famous papers, which are now, my God, they're 50 years old, but they're really important, right? We think about today, look what's happening right now in Germany, right? This big surge in the price level. It looks like inflation, but it's not really inflation because we haven't seen several years of higher rates of change, but workers have lost real wages. So they got the price level wrong, and now they're trying to claw back, and there are going to be strikes, and there's going to be, battle of the markups. And if the central bank doesn't accommodate it and raises interest rates, it probably won't lead to more inflation. But that's exactly the kind of thing that these guys were talking about back then, when the central bank was much more accommodative and didn't worry as much about inflation as they do today. Okay, so now I'd like to talk about a particular example of learning, and this will, it's a micro application, so it doesn't have to do with the business cycle, but it has to do with how the wage distribution for an individual worker is not necessarily time invariant. And Jovanovic's approach was interesting because he was trying to look at labor market facts that we see that we thought we explained using the famous Burda-Mortensen model. Remember, Burda-Mortensen said, why do wages rise with job tenure? Okay, and they can explain that, right? But it's just luck. It's not because you're better. It's just because you didn't get a good offer. You didn't get fired. You got good offers and you got pulled up the wage distribution. So again, interpreting the wage, interpreting again, different interpretations of what a firm is and what a match is, but generally, people who have been working a longer time have not gone into unemployment will tend to earn more money, either at the same firm or at a different firm. And Burda-Mortensen's not so good about distinguishing those two, but it turns out that tenure matters. So how long have you not been unemployed? That would imply higher wages. That's a fact everywhere. And Burda-Mortensen tried to explain it in a very, very clean, homogeneous worker way, but there are alternative explanations. We talked about it in a previous lecture. It could be human capital. So the longer you work, the more experience you have, you've acquired specific and general human capital, of course you're going to be more productive. The problem we know in the data is when you change your job, you take a hit. You earn a little bit less. So that's another labor market fact that Burda and Mortensen do well in explaining, because you always have to start from scratch, right? Here, human capital should matter. So if you're a doctor, you get fired because your hospital closed, you get another job, you probably started at a lower wage, but you're still going to have a wage that reflects your medical training. That would be true for a welder or an electrician as well, or a school teacher. Okay, we also know that quits are negatively associated with the length of time on the job. So that could, Burda-Mortensen, that was a reflection of bad luck. You didn't, or good luck. You didn't, if you quit in the Burda-Mortensen model, it's because you got a wage offer that was better than your current wage. And bad luck would mean if you're making a lot of money, you're not going to get many wage offers that are better than what you have already just by construction, by the way the model's built. It's a stationary search model. In fact, it is true in general in most countries that the longer you work for an employer, the lower the probability is that you're going to leave it at all. So the conditional hazard rate, given that you've been with a job for maybe 30 years like me, is pretty low. Okay, so that's one explanation is Burda-Mortensen. Another might be just maybe there's something about that match that is pretty good. It's sort of a qualitatively better match than the other matches that are out there for someone who's just starting, or maybe someone my age who tries to match with this university. And of course, we all know that quits are negatively associated with the wage. These are all things these are labor market facts. They're very robust, and models have been trying to pick this up. We already hit this. We hit this in our class on advanced labor economics. We also talked about just the general idea that the match might be specific in the sense that maybe relational capital grows in a deterministic way. You sort of become very productive with somebody, with your unit, with your firm. And if you lose that job, if the firm goes bankrupt, you're going to have to start from scratch. So that's, even if you're very talented, you have general human capital, which is transferable. You have specific human capital that's industry specific, which is transferable if you stay in the industry. And then there's firm capital that may just be related to the firm, the way they do business, the way they work on the assembly line, all these things. So that's an old idea. That's been around for a long time. We already talked about luck, right? The luck is, there is a bit of luck in everyone, and some people are unlucky. So, and that's what we've spent a lot of time thinking about Burda and Mortensen. It's a great model. It really is brilliant, even if you don't like the bare bones wage distribution. You can soup it up to give a more realistic G in that case. Now, third alternative would be that we just don't know. When we first go out on the first date, we don't know if this is going to work out. And this is why now companies spend a lot of money on recruiting. They have like assessment centers. You spend a whole day with the company and everybody looks at you and you have lunch with them and then they grill you with some questions and then they say, no, you're not the right person. Bye. Usually now they just say, yeah, of course, because you guys have a great labor market right now. So if I had given this lecture 3 decades ago, it would have been exactly the opposite, right? And that's like the V over U mega macro issue. But this is, the fact of the matter is, even in the United States, where it's easy to fire workers, it's like getting married. It's a little bit like getting married. If you invest resources in a job relationship with a worker, you don't want to throw it away in 2 weeks. Okay, so we'll talk about that in detail. But just to give you the general idea of learning, before we go into this beautiful model by Jovanovic, I'd like to discuss kind of a generalization. I think this is a nice place to put it. This is one of Sargent's students. I think he's in New Zealand now. They've written a kind of a textbook that's just out. Like nowadays, you can write a textbook and just put it online, and it never has to get published. And I have the 2020 version, but it has lots of holes in it. We're saying we'll do this later. We'll do this later. But this is a really nice extension that you can understand. It involves Bayesian learning. Okay, so here's an example of you take your old model that we know, except now you have 2 different distributions, and you become unemployed, and you don't know what distribution you're being faced with. You know there's just one, okay, but you're in this bathtub, you're in the F bathtub, and the F could be F1 bathtub or the F2 bathtub, you don't know. You just landed in this bathtub and you're swimming around, and you have to infer which bathtub you are, and given that inference, you know what those 2 distributions are, and if you knew with certainty one or the other, it would be very easy to derive the reservation wage for that case. But if you don't know, then you have to sort of mix it up. Because people aren't stupid. People are kind of thinking about this. And this is kind of the way I like to think about workers who they know things have changed around them and they have to revise their reservation wage. And what, if they were Bayesian, what would they be doing to face that problem? Okay, so the idea is you have these 2 distributions that are known to the worker, but they don't know which one they're facing, and they have a probability of being in the F1 bathtub or the F2 bathtub. Okay, and once they're in there, they can't get out, so that's their fate. And they have an initial probability that they're in the F1. We'll call that pi, and 1 minus pi is the probability of being in the other one. Okay, and the idea is you're going to use Bayes' rule. When you draw a wage, I'm going to try to, okay, this is a really lousy wage. Does it mean I'm in a lousy distribution, or do I want to hang in there? And well, there's a right answer to that if you take Reverend Bayes' approach. Okay, so the density you would use to compute the reservation wage, if you're risk neutral and all the other things happen in this model as if we did them, continuous time, etc., you would use the following density. It would be a weighted average of the 2 densities. Because you're just sticking your hand in this, you're meeting, encountering, and you're sticking your hand in an urn, you're pulling out a wage offer, you don't know what the F is. It's going to be F1 or F2, and I have these ex ante probabilities which I'm computing in a very intelligent way. So after I draw the wage, I'm going to update Q. Okay? So it's a very simple extension, and it gives us non-stationary search, because over time we will adapt. You know, it could be the case that in a rich labor market experience, you might actually have the feeling, hey, maybe I should have held out for a better wage. You know, I look around, I see all these other people getting better wages. Maybe, so in a sense, if I get according to this model, I'm going to have a reservation wage. I may have a kind of regret if I'm told the truth afterwards. Hey, you know, you really should have taken a better. You should have said no a few times. You would have gotten a better. But anyway, you know, given that you don't have that advantage in time t, what do? So I like this. Okay, so Bayesian learning would say I update given what I observe and what I draw. So if I'm going to basically adjust my pi t plus 1 as a weighted average of the conditional probabilities of the two events that I observe. Okay, so I'm basically, you can see pi t plus 1 is an equation of motion for pi t. I start with an initial guess, and after I observe the wage, I'm going to adjust my pi t plus 1 using Bayes' rule. So beliefs, again, starting with a belief, what is a belief? Belief is a pi. Pi 0, pi 1, pi 2, starting with t plus 1, t plus 2, and I'm basically, you see pi t has a trajectory through time depending on the draws that I get, the w I get. And again, I can accept or reject, but I can use that to calculate a new a density for the next period, and I can solve for the reservation wage under those conditions. Okay, so that's a very simple example. You can write down the Bellman equation using the Sargent type of, the Lundquist-Sargent notation, which we've done for the cheese stand problem. Okay, so the Bellman equation would say that V star, the function V star, solves this functional equation, the maximum of either, and again, this is the case of no firing, so you're in there forever. So going back to the very beginning of the course. And there's, in the next period, you get a chance to go and C as a search cost, so you can jazz it up a little bit and add some stuff. And this is a fully recursive problem, but it doesn't have it implies basically a reservation wage that has a trajectory over time. Okay, so now let's talk about Jovanovic. Jovanovic is the purpose of today's lecture, basically. So it's the notion of taking this learning, this very similar to what we just talked about, but much easier to manage, to think about what the match is. So until now, we've always talked about the worker basically independent of what the firm does, making her decision. And in fact, it might be the case that the firm and the worker have certain match qualities that are maybe difficult to reproduce elsewhere. So the firm knows that, the worker knows that, maybe that could explain some of the behavior we've talked about, this rising wages for tenure, for workers that have high tenure, and that quits don't rise with tenure, they fall with tenure. So we can think about basically a possibility that workers and firms have a special sauce. You know, they have a special quality of working together, but they don't know immediately if that's going to happen. It takes some time. You have to learn about it. So this is a model that basically doesn't involve any wage posting. So we're going to go back to the Chicago approach, which says that somehow you have this productivity that we can observe and agree on, and then you just get this productivity. So it's I think it's a bit of a cheat in the sense that if a worker knows that the work that she or he has bargaining has productivity, then this gives them certain bargaining power over this surplus that the firm might want to share. But in this particular setup, we're just going to assume, as we did in the Rogerson-Scheimer Wright, that workers just get their productivity. So again, it's a bit of a cheat, but maybe it's a simplicity. It's an element of simplicity that helps us get further to the message. The message is that if I observe the worker's productivity in a period, it may not be perfectly indicative of what the long-run productivity is. So again, it's a signal extraction issue. I mean, maybe the worker just had a bad day or a bad week or a bad year. You know, you always have these evaluation meetings when you have a job. You have to, what do they call them? There's a word for it in German. Like, you know, discuss your progress or whatever. Anyway, it's like it's a big deal, and usually it's a signal whether they keep you or not, that sort of thing. So Jovanovic is going to exploit this. He's going to say we observe a signal noise mix, and we need to extract the signal and kind of try to ignore the noise or try to filter out the noise. And this goes back to a really old idea, even before Robert Lucas. It's just if you have two normal random variables and you add them together, okay, and if you know something about the variance of the two and the covariance of the two, you can compute an optimal forecast of one given the other, or you can compute an optimal forecast of a component of the sum given the sum. Okay, so Lucas pushed this to the max in the 1970s in his famous papers on monetary neutrality. So, and we've been using this ever since. Okay, so Robert Lucas, but it's actually statistics 101. Most statisticians look at this and they say, yeah, this is obvious, but economists kind of discovered that it does have some really powerful economic implications. So if you have X and U are normal, and agents can observe, say, the sum, okay, or they can observe one and then try to infer the other, given that one is a linear combination of the other and some randomness or many different variations of that theme, then it turns out that in the normal case, it's a linear function. So it's like the OLS regression model. It's like I observe X, what's my best forecast of Y? If I know that X beta plus U is equal to Y, right? And I only observe X. So, I mean, it's kind of, except in that case, it's pretty obvious. But here you observe the sum, so you observe Y, sum of something you can't observe but you're interested in, and the other is some randomness. And you know the distribution of those two variables, and since they're normal, you can describe their variance. The second moment is a complete characterization of everything that's above that. So it turns out that if you can observe Y, then you can do a best estimate of X given that Y, and given that you know the variance and covariance of X and U. Okay? I'll show you the formula in a second. You should just let it sink in. The cool thing is linear. That's the cool thing. So in the Lucas case, it was like the agent observes the price of her good that she's selling at the flea market, and she doesn't know if it's because of inflation it's going up, or is it because the real value of her hot dogs. If she's selling Bratwurst at the Weihnachtsmarkt, okay, and the price of Bratwurst goes up, she's not a price setter. This is the strong version of Lucas was the price. Even those guys are competitive, but you have this own price, and then you have the price of all the goods that you're going to consume. Because after you sell the Bratwurst, you're going to take the money and try to buy Glühwein, popcorn, a ride on the Ferris wheel, etc. So what you care about is the real price of your Bratwurst in terms of the price level of everything else. And Lucas said, okay, suppose Both of those things are log normal. So if I have a price level times the relative price of my good, and I take the log of that, those things are normal, then obviously I can use in a very simple way the observation of the price of my bratwurst, which contains some inflation, to decide how much should I produce and work hard, expend effort to take care of. So that was the Lucas idea. Very smart. Got a Nobel Prize for that. Jovanovic says, let's try this. I'm going to observe some productivity in the first period, and I have to figure out, and this is, when I say I mean the employer and the boss together. The boss, employer, and the worker together have to decide whether this is a good match or not. So that's the cool thing about this. And again, Jovanovic is downplaying the conflictual element of the employer-employee relationship. It's just talking about trying to do the optimal signal extraction and not trying to see when we should go on strike or whatever. Okay, so the ingredients, and again, I'm going to use the Sargent notation just to keep things clean, very similar to what we did at the very beginning of the course. Think of this as a model about job matching or job assignment. So, you can extend it and make all sorts of other macro type of aspects, but this is just a simple partial equilibrium problem. So think of labor as being an experience good. We're going to shut down employment afterwards. So, if you accept, you're there forever. It's like getting tenure as a professor. Again, it's just to make it easier to understand. And there's no on-the-job search. So all these things have been shut down. But there are a lot of papers that have tried to, at the cost of a lot of complexity, to add these. And there are no other frictions. Risk neutrality, profit maximizing firms, workers have information on the underlying model. They just don't know what the quality of the match is when they first meet. And again, Chicago assumption, wage equals productivity. We're not going to have a Nash bargain. I don't see why that would affect things at all. And again, it's like the stepping stone and the Rogerson, Chimer, Wright on the way to it on the job search model we did already in class. Okay. So the way to do this is that you have to remember, you always have to start at the back and solve recursively to the present. So you take the end of the model, the last period as the starting point. And there are 3 periods. So without starting backwards, I'm just going to give you the 3 periods first. The worker decides the reservation wage, given the Chicago assumption that when the productivity is observed, and productivity is noisy, so it's going to be given the x plus u. Again, think of this as, if you like log linear, think of this as the log of big X times big U, and these are like logarithms. Then you can think of it as percentage. U is the percentage deviation that is confusing me, the noise, and X is what I really care about, right? X is what I'm going to get my ultimate wage based on, and both firm and worker have an interest in paying the worker her productivity, expected productivity conditional on the noisy signal. Okay, and then the workers set this strategy first, and then they go off and they meet this firm, and the firm, and they pull out a thing called productivity out of a hat, and this is maybe think of this as the how well you did in the first year of your job, and it's the sum of a signal and an orthogonal uncorrelated noise. So the noise is uncorrelated with the signal. That's an important part of the paper, or the model. The noise is just literally noise. It's confusing, but it's not affecting the mean. And you can always redefine productivity to take care of any sort of systematic part of the noise. So this is not a crucial assumption. And at this point, the worker and the firm jointly accept the match or reject. Okay? And then, after the first year, you observe productivity with certainty. And it's still random, but you observe it forever. And then you can decide, okay, I'm going to leave because maybe you weren't that good in the match. Maybe the match was pretty lousy. So you can still have a separation after the second period, and the third period comes, and you observe the true productivity, but then it's forever. And the worker either separates or stays forever. So it's really simple. Because that last period you can solve for first, and you can move back to the second period, and then given that, you can solve the reservation strategy for the worker in the first period. So that's the Jovanovic model in a nutshell. I tried to draw this picture to make it more clear, maybe. Here are the decision stages. So you can think of it as a three-stage model. We had 3 periods in quotation marks. I mean, it's not clear why it's really a period. I mean, you can solve this problem relatively quickly. It doesn't have to be a lifetime, but it's like you start, and then you have this trial period, and you have the final resolution of uncertainty. So we have to start at stage 3 and solve that one first. That's the key aspect of this model. Okay, and doing that, because then effectively you can solve for the distribution in stage 2 that will condition your reservation wage strategy in stage 1. Okay, so we'll use notation that's kind of similar, but not exactly similar to what we've done before. And this is a discrete time model. There's no Poisson arrival. All these things can be added, but at the cost of some complexity. So you have this B, that should be familiar, and then I'm going to use this x tilde to be defined as the sum, just so we don't have to carry around the sum in the expressions. So x tilde is x plus u, and u is orthogonal to x. That means that the expected, I mean, u has a mean and x has a mean, so the covariance of x and u, which would be the expected value of x minus the mean of x times the u minus the expected value of u, which is 0, is going to be equal to 0. They're really uncorrelated. So knowledge of u doesn't help me predict x. It just makes the sum noisier. So if you've seen the Lucas model, this looks very familiar. The joint normality assumption, of course, is crucial to get the linear decision rule, but it's not necessarily, it's not going to change the logic very much. It'll make it much more difficult to solve. I do think the uncorrelated part is crucial. But again, it's a pretty robust model. And we're going to assume that the worker is clever enough to know this. Okay, this means basically a decent assessment of own talent in the sense that the mean of the distribution is equal to the correct mean, but there may be some variance. And then the expected value of the noise is 0. So it could be a really good day, I had a really bad day. On average, I have and this is the log, that means that the expected value of the log normal piece is equal to 1, right? So on average, you're getting it right, product. Okay, so the symbols, we'll use sigma to denote the variance of the 2 respective pieces, and therefore sigma xu is equal to 0. That's clear. That's the orthogonality assumption. We call that. Okay, that should be familiar to you from econometrics, which you've had infinite numbers of results that depend on orthogonality conditions, method of moments, etc. Okay, so this is not, if you read Jovanovic, you won't have this notation, but the model is this, basically, stripped down. So here's the key result that you should remember for your life, okay, which is that if I observe x tilde and I want to make a good forecast of the best forecast, given normality assumptions and everything else we've assumed, it's simply a linear function of a constant, consisting of a constant and another constant times the deviation of the signal from the expected value. The x tilde, the signal plus noise, random variable minus its expected value. And if you look at that carefully, it looks like a regression. You know, it looks like a regression equation, univariate regression. And you can actually find that more than just convincing. It's actually the so-called regression coefficient for B would be literally what you would get if you had a lot of data on X after the fact, because you can't observe it in the period, but you might be able to observe it in a couple of years, and X tilde, the noisy signal that you're getting, okay? Does everybody see that? Remember when you have X and Y and you compute the regression coefficient, it's going to be the covariance divided by the variance, covariance of Y and X divided by the variance of X. This is very similar, except now it's either a theoretical statistical quality that you just know because you're smart, or if you had lots of data from the past on other friends that had the same characteristics as you could actually literally calculate this. So look carefully at this and see what it means. B will depend on the covariance of the noisy signal with the actual signal. So if there's a lot of noise, what's going to happen to B? Yeah, and the limit, if the covariance is 0, suppose U is extremely noisy, then this observation of the signal plus the noise is worthless. So you'll attach no value to it. You'll ignore it, basically. And if the signal is very precise, suppose U has a variance that's going to 0, then your observation is a very precise indication of what X is. And then the B would tend towards 1. So B is kind of bounded by 0 and 1. Maybe on the closed interval if you think of the limits, but generally it's going to be between 0 and 1. Okay? So that's a really cool result, and it's used a lot in economics in a lot of different applications. You know, you have something that's noisy, you have something you're interested in, and you can even think of the Kalman filter as a time-varying variation of this thing. I mean, it's a similar idea. Okay? So it turns out that's given the orthogonality assumption we've made, that is the signal-to-noise ratio. Okay, it's a transform of variance of X divided by the variance of U. And that's why those two things in their relative sizes determines how much you pay attention to the signal. So this is kind of what's going to drive the model in Jovanovic. And this forecast that you make, given the X tilde, is normally distributed. And it's informative. It's worth looking at. You'd be willing to pay to have this job interview because it gives you a chance to see, well, did I miss something, or was it worth it or not? Now again, the Chicago assumption would say that you get the worker's offer or the wage the worker is paid is simply this conditional estimate. So again, this is assuming a lot because it implicitly, if the worker can threaten to leave, this would be its fallback position, and I don't think that's in the spirit of the model because you have to have another date and have another job interview and assessment center, et cetera. So this is not exactly consistent, but you know, we'll take it for what it is, just to make the point of the model. Okay, so that's going to be the worker's wage conditional on observing the signal. So you go, you have your interview, they say, we'll let you have a probationary period for 1 year, and then you get this X tilde, that's your productivity, the boss's assessment of you after 1 year, and maybe it was really lousy because you were sick a lot or you just didn't get along with your colleagues, but it might be noisy, so maybe we don't want to get rid of you right away because maybe your true productivity in the end of the day, when we actually observe it, will be better. It could also be worse. Okay, so we can calculate the variance of this, estimate of your productivity conditional on the signal. And that's just going to be a constant times sigma squared x. So depending on how variable sigma squared x is, I'm going to have a large variance or a small variance, and that's going to condition my reservation wage, or the reservation decision rule that I'm going to take. Because the whole reason we're doing this is because when you get that, when you meet and you get this noisy signal, you have to decide, well, do I stay or do I go? If I go, it's like rejecting a wage offer. It is a wage offer, but it's based on uncertainty. It's based on this uncertainty that will be resolved in yet another period. Okay, so you can see that this kappa is another important part of the model. Kappa is going to be extremely important for basically determining, remember the variance of the wage distribution affects your desire to stay or to go, because you're not going to get this wage forever. But you know, if there's a prospect of getting, this is a productive match and you just had some bad luck, you'd be better off staying, right? And the employer agrees with you. It's like a super nice employer says, you know, you've had a tough year, but I really think you're good. I think you're an excellent worker. Or it could also be, you know, you had a great offer, you had a great first year, but I think you're full of baloney. I think you're not going to be very. So this is going to depend on this variance of the noisy signal. And this thing is known as the signal to noise ratio, kind of an important characteristic of the model. So the problem is easy in the last period because you observe it, right? So it's clear, you know, you basically accept it or you reject it, and your true productivity could still be very lousy. You might have had really a great first year, which just completely belies the true productivity you have. But once you observe that, if you wait till the last year and this is the last period and you observe it, then both can agree, no, this is not going to work out. So that this problem is known to us. It's trivial, right? So it just depends on the value of being unemployed relative to the value of working at this job forever. Okay, so we can figure that out rather quickly, and we can derive this reservation wage in the last period, just solving that problem. Okay, so we need to know what people get if they're unemployed, so they have some sort of benefit, and they have the option of getting another offer in one period, and a similar noisy signal, etc. Okay, so under those conditions, you would just solve, given the last period, you could solve for the reservation wage in the noisy signal case. Okay, and this means that we're going to use, to integrate over the wage offers, we're going to use this conditional distribution given the fact that I've observed this noisy productivity. Okay, so this is it's again, it looks complicated, but it's not. It's the same reservation wage problem we've had before, except now this this density, df, is conditional on an observation. So I have to know what x tilde is first before I can compute this. That means for every value of x tilde, I'm going to have a different density of the final productivity. Okay, so we have the same problem in the second period, and we're going to solve using this value function, which is given on the left-hand side of the equation at the top. Okay, So basically, the model's going to predict that I'm going to observe this noisy signal, and I'm going to have this reservation productivity, and it's going to be depending on, it's going to depend on the distribution that's implied by the XR, and I will accept any offer that exceeds, or any observed signal that exceeds that reservation productivity level. Okay, so finally, we need to go back and ask the fundamental question: where does this utility of unemployment come from? Because once we've derived the reservation wage, we still have to go and find out what value of utility is consistent with that from the beginning, given that we have this conditional observation and decision based on the known parameters of the problem. So think of this as this value of utility must be based on the conditional value of the problem given by V of x tilde over all values that exceed the reservation wage, which the worker has effectively solved for at the very beginning of the problem. Okay, so we can think of that conditional normal density of x tilde as being decisively important, and it's going to depend on, because it's normal, it's going to depend on the mean and the variance of the underlying problem, because the workers know ultimately what the distribution of the signal looks like, and they know what the distribution of the noise looks like, and therefore they can infer this distribution from the beginning. Okay, there's a slight issue of timing at the same time. So this is the way of closing the model and getting a value for U, which ultimately started, we started by saying, given U, what would be the optimal accept or reject policy in the last period when you observe your true productivity, given that U exists, but we never solved for U. So you have to sort of close the model by solving for that at the end. Okay, so the model has it's all theoretical in the sense that we don't have any closed form solutions, but you could use certainly numerical methods to compute values for these things under certain parameter values. If we assumed a value of B, for example, the income and unemployment, a particular value of the mean and the variance, and these are normally distributed covariates, so it's already putting a strong set of constraints on the setup. You can actually solve for these things numerically. Okay, so what does the model do for us? Well, we have some matches that are accepted in stage 2, which are not so great. Okay, so we have false positives. We took this guy on, and he turned out to be a rotten egg, okay? And then some people we might regret, well, we turned them down, but they went off and became really successful. So you're going to have, you can actually compute those rates given the distribution of the noise and the underlying signal. And you can imagine the higher the variance of the noise, the more likely you are going to be making these statistical mistakes. It's like getting vaccinated and you still get sick, or if you didn't get sick, even though you weren't vaccinated. All these things happen in this model. Of course, the good thing about this model is that the bad matches always get found in the end after uncertainty is resolved, all the chaff goes into the fire, and all the grain gets harvested. But so to implant this into a general equilibrium model, you'd probably need to have some separation that happens anyway, because otherwise all the duds end up in the bathtub, and then the workers will never get a job offer, right? So there has to be some renewal, or maybe new workers come into the bathtub. And we encountered that with the Burda-Mortensen problem. The Burda-Mortensen problem had the same issue. If you just have luck, then everyone will get the top wage at some point. They just have to wait long enough. Okay. So the key thing you should remember is that you use backward recursion to do this. You solve for the last period given you, get a cutoff value for the final period when you observe the true productivity, and that's an easy one. We did that at the very beginning of the course, and then in the middle part, you have to take that value, the value of being in that last period, and then compare that to the decision rejecting a match that is coming from a noisy distribution that we're not totally sure about, but it's worth maybe betting on a horse occasionally. So it results in this fantastic conclusion, which I think is nice, is that the final productivity, XR, is greater than XR tilde. Think of XR tilde as that's the reservation wage for the final period, the reservation wage in the second period. Those are going to correspond with the observed productivity. So you're going to have this rising productivity with tenure, which is what we wanted. Again, productivity is not equal wage, except in the Chicago world, so be careful, but it's not a bad indicator. Workers, remember, if workers are not productive, firms that hire them and pay them too much are not going to survive. That's the survival, the Malthusian, economics. It's true. So we do think that workers who have, they may get paid a little bit more or a lot more than their productivity, but not for very long. So if you're a CEO of a really successful company, maybe there's a causality involved, but at some point, these guys don't stay in there forever. So they don't, they do a lousy job, they're going to get fired. I think that's a fair, you get rising stability almost by construction. What I don't like about this model is that when your productivity is ultimately revealed, it's forever, And you have the marriage of the dream marriage, you'll never separate. So you it kind of cooks the answer, but I think it's a pretty good setup. Okay, so Jovanovic accounts for a bunch of other labor market facts. Tenure and wages are correlated at a particular firm. So you think of the firm as this sorting out of the quality of the match. Quits are negatively correlated. So you can interpret a quit in this model as a separation. There is no difference. There's no exogenous separations. Quitting means just doesn't work out. And high wages today would also be negatively correlated with subsequent quits. Okay, and you can think about the alternatives and think, well, the world is probably some mix of the two. These are all very useful models to think about that. Okay, so this is the famous alternative to models that just say it's all about human capital, because we know that when firms close or when firms have mass layoffs, if you follow the workers' wages who were at that firm, they drop for sure. So there's a loss of they call it the wage separation loss, or it's just well known, and it's true in Germany as well as the United States. This is an alternative way of explaining that fact. Now, there are a lot of critiques of this model. So, I mean, obviously, the critiques of all models. People, if they do quit, they don't quit into unemployment. So interpreting the separation as a quit is a bad idea. It's probably a mutual separation. And that's because workers and firms are assumed to have the same assessment of their own ability. Oftentimes, the firm says, "Look, you're not doing a great job. We're going to have to let you go. And the worker says, I'm doing a great job. What are you talking about? You know, why are you letting me go? So you have this disagreement. It's not possible in this model. Everyone knows everything. It's like Mortensen Pissarides. Everyone kind of observes everything. So the real world is maybe different. And the firm has reasons maybe to dissemble and possibly misrepresent the worker's productivity. If the overriding objective of the firm is to reduce employment because of a business cycle change. You know, it's funny, we talk about this now, it seems like it's insane, but 20, 30 years ago, German firms were trying to get rid of workers. Now they're complaining about not having enough workers. So, I mean, I've been around long enough to see the whole cycle, which is really interesting. I mean, really, unions were complaining that firms were trying to shrink their size and get rid of good employees, but now they can't get enough workers. We're Arbeitskräftemangel everywhere. So, yeah. All right. So that's one critique maybe, and then it's probably a better model for the micro wage tenure relationship and the job loss upon separation that we observe even in Germany, but also especially in the United States. It just may be a nature of the quality of the match. And you might criticize this wage equals marginal product of labor. Again, I don't know the right alternative to that, but it's, there are ways of salvaging it. You could say that inside the firm, there are many different matches. So you could transfer the worker inside the firm to a different job if productivity goes down. Like you get hired at the IMF, and after a year they say, well, you're a great economist, but you're not going to be very good in our research department, so we'll put you in the Antarctica department. And that's a reflection of your productivity. And then, of course, you can have the option of leaving, which a lot of people say, well, I'll go work for Chase, Citibank or whatever. That's just trying to be funny, right? Okay. So this is, I went a bit quickly, maybe. We can come back and talk about it if you want, but these are the key things to worry about. And if you're interested, take a look at the Jovanovic model. It's a bit difficult to read, but I think what I gave you is kind of the essentials. Okay, good. So, any questions? No questions. So we're a bit early. Thanks.